Hello, and welcome to another lecture in ECEN 215 Principles of Electrical Engineering. The topic today is power in AC circuits. So what we're going to look at is how do we examine power in a circuit using an AC power source. So obviously now we have a frequency component, we have circuits that have inductors and capacitors and resistors in them, so we have complex impedances. So how do we analyze the power being consumed, absorbed, and or supplied by the circuit? Because these devices now, these inductors and capacitors, they both absorb and supply energy. So we need to look at this a little bit more carefully than just simply going power is equal to voltage times current. But effectively, it's very similar to what you would think it would be. So let's first take a look at power and current and the voltage. So obviously, Ohm's law still applies, everything that we're doing. Current is voltage divided by the impedance. Here we have voltage magnitude of phase angle of 0 at some frequency, some radians per second, divided by the magnitude of the impedance and the phase angle of the impedance. And because of the division, we get Im, which is Vm over the magnitude of Z, with 0 minus the phase angle. So there's a lagging component here. Whatever the impedance is going to subtract that angle. So whatever this angle is would be minus this angle. So this is how you would get this. So using that, obviously magnitude again, is just voltage magnitude over the magnitude of the impedance. And for a purely resistive circuit, we just simply have V of t equal V magnitude cosine omega t. So our typical cosine equation, I of t is the I magnitude cosine omega t. And simply, if we just solve for standard power, V of t and I of t, we get Vm times Im times cosine squared omega t, which looks like this. The power average ends up being Vm Im over 2, as you would figure, because it is being absorbed, and it's because of this term here, we end up with this Vm Im over 2. So if you notice, the frequency has doubled. This is a trigonometric identity here. So that's basically we have our two waveforms. Obviously, they're perfectly in phase with each other. So no matter what the phase angle is, if this was plus 25 degrees, then the current would be plus 25 degrees because of pure resistance, and therefore they're perfectly in phase. But the frequency has doubled in this case. For an inductive load, now this is a purely inductive load, and we're going to cover in a few moments what we call an RLC circuit, which is truly a complex circuit with all sorts of different inductance and capacitors and resistors. But what we looked at a moment ago was purely resistive. This is purely inductive. So here we have an impedance that is just omega L with a phase shift of 90 degrees. And here we have, current is V over Z. And here we'll have Vm is equal to cosine omega t. The current is now whatever the magnitude is. Now it's cosine omega t, but it's going to only be phase shifted now by minus 90 degrees. You can also just write this as Im is sine omega t. Trigonometric identity here because cosine is equivalent to sine. And so power is voltage times current, and we end up with the magnitude of the voltage and the magnitude of the current times cosine times sine, which ends up using the trigonometric identity 1/2 sine 2x. So it's a phase shift version. So we end up power t Vm Im over 2 sine 2 omega t, which looks like this. So here we have some of the power is being absorbed and some of the power is being supplied. So remember from early in the semester when we talked about positive power and negative power is where the element is absorbing power from the circuit, and negative power is where the element is returning power or sourcing energy back to the circuit. Here, the energy is being consumed by the inductors, being absorbed, and is storing the energy in the magnetic field. Here, that energy is being released back into the circuit, being supplied into the circuit, different phrases of the same thing. So it's being released back into the circuit, and hence it's negative power. And so obviously a purely inductive load has no net power consumption, if you will. The net power is zero. The average over time is zero for purely inductive. But it is consuming power, but it's also giving it back the same amount. And of course, this here is Vm over 2 sine 2 omega t. Again, notice that the frequency has doubled. For a capacitive load, impedance is 1 over omega c. Now the phase shift is minus 90 degrees instead of plus 90 degrees for the inductor. And we end up with the current is equal to V over Z. So no real surprise in any of this, everything that we've covered so far. Again, same process now. Instead of being where we were subtracting 90 degrees, we're adding 90 degrees, and we just end up with minus Im sine omega t. So effectively, everything that we just looked up for the inductor, but it's now for the capacitor, it is just inverted, because now we have minus Im sine omega t. All we did is just, because sine is omega t minus 90 degrees, now we're adding 90 degrees, so effectively you took a sine and shifted it by 180 degrees, which is negative sine. So power VIT is minus Im cosine omega t sine omega t, which, using the same trigonometric identities we had a moment ago, is the same equation we had for the inductor, just with the negative sign in front of it because it's just inverted. So minus Im over 2 sine 2 omega t, which again, very similar to what we were just looking at, just phase shifted. Here, positive power again is the energy being stored into the electric field. So the capacitor is absorbing or consuming energy and storing that energy in the magnet or in the electric field. And then when it is returning the energy on the negative power side of the cycle, it is returning the energy to the source back into the circuit. And again, it's just minus Vm Im sine 2 omega t. Again, note the doubling in frequency. So it's important to pay attention to the true reactive power. So what we were just looking at with inductors and capacitors is a reactive power, because the net, if you took the average power of that cycle of a purely inductive, purely capacitive load, obviously the average, the mean value was zero. So if we put a pure inductor on a power line and just allowed it to cycle, and we go, well, I don't need to really size this power line correctly for this inductor because the power loss through the inductor is it's a perfect inductor. It's 0 watts. So therefore, mathematically, I shouldn't have to worry about any sizing of cables or worry about voltage or anything. I mean, it's 0 watts, right? Wrong, because what's happening is there is still current moving to the inductor and then back from the inductor. Granted, the average power at that moment is 0. That energy is still flowing back and forth through the circuit, and hence you have to pay attention to that in design. So you always have to know what is the actual currents that are flowing and make sure that your power lines are capable of handling that. And this is true even for the systems that you are going to be involved in your particular discipline. You have to make sure that the power connections to whatever device you're working on can handle the actual currents that are flowing through in the sense of the size of the wire, and for the sense of insulation, you got to pay attention to what the voltages that are going on. So this is very important that you do this, even though maybe the net power is low, you still could be having large peaks. So now we're going to talk about all the different cases of dealing with RLCs. Now this is a general impedance-based circuit, so you have resistors, capacitors, and inductors in a circuit. So you truly have a complex impedance now. So for the average power, we still have V times I of t, V of t times I of t. But now we're going to have, say, V of t is just going to be some magnitude cosine omega t, and I of t is going to be Im, which is going to be obviously related to the impedance magnitude. And then there's going to be this phase shift here, this current magnitude with a phase shift between the two. This so far we have been doing in all of our circuit analysis up to this point, so we know we can get to this point here in our calculations. And power is just simply Vm times Im, so our two magnitudes, times cosine omega t times cosine omega t minus theta. What is the phase difference? Which, after using various trigonometric identities for these two cosine terms, we end up with Vm Im over 2 times the cosine of theta. So theta here is the difference, or is the basically the difference in the phase angle between the voltage and the current. So this little phase shift here, because this is assumed to be 0. So whatever this phase angle is, this is the difference in that. So this is the, and I'll show a slide on that in a minute. So we have this theta here. You can also rewrite this as VRMS times IRMS cosine of theta, and that is because VRMS is Vm times over the square root of 2. IRMS is I magnitude over the square root of 2. If you take the square root of 2, multiply each other, you get 2, which is effectively replacing this half component here in the denominator. And so you just end up with the two RMS terms here. So using that, we end up with this equation for power, VRMS, IMRMS, cosine of theta, where cosine of theta is known as the power factor. If you ever work in an area where you're dealing with a lot of motors, three-phase motors, so on and so forth, you're going to see the phrase power factor. Like this motor has a power factor of 0.9. Well, that is actually giving you what theta is effectively, because they're giving you the cosine of theta. It's going to be a number between, I guess, in the end, -1 to 1 is truly the cosine of theta, where theta is known as the power angle. So in some of the homework and or on the test, you're going to see things like, given this circuit with a power factor of, say, 0.7 or a power angle of 25 degrees, given VRMS and IMRS, what is the power? You should be able to solve that because you would know that if you're given a power angle, that you would go and plug the theta in here, get the cosine of that, say 25 degrees, and multiply it by your RMS values. Theta, again, is just simply the difference between the voltage and the current. So if voltage is 0, then it's just minus the current angle. That's all this is. So you're looking for the net difference between the two. So if you have a phase angle for the voltage and a phase angle for the current, you would use that to get your power angle. Sometimes it's stated as a percentage, and that's just because, again, cosine is all about plus or minus 1. And then what it is they say to kind of give you the negative and positive part. Current leading, capacitive, basically it's a capacitive load. That will be your negative. If it's an inductive load, it lags. So a typical power factor would be stated like 90% lagging, which means that the cosine of theta is 0.9, that the current lags the voltage. So if you have something that is 90% leading, that means that the cosine theta would be minus 0.9. So that is, if you see terms like this, then you know what this means. For a general RLC load, the reactive power, which is the imaginary component of power, is defined as a Q, and it is the VRMS IRMS times the sine of the power angle. And this has the units of VARs, volt ampere reactive. And you will see this if you're ever working in with motors and or large capacitor banks on power lines and things like that. You will see things listed in VARs or kVARs. So volt ampere reactive. The apparent power is defined as VRMS times IRMS. So that is what is basically appears to be, if you will, the net power, if you will, the vector. And I'm going to have to show you what this means in a second. It has units of volt amps. So we have the power, which is in units of watts. We have VARs, which is the reactive power, and it is volt ampere reactive. And then we have parent power, which is in volt amps. And it is simply the P, the power part, the real power, plus the square of the reactive power is equal to the square of VRMS IMRS squared. So essentially Pythagoras theorem, parent power square root of this. So parent power is equal to the square root of P squared plus Q squared. So again, there are three units that we're tracking here. There is power, reactive power, and apparent power. So we have units of watts, vars, and voltamps. Again, watts, vars, and voltamps. This is telling you the real power. This is telling you the reactive power or the imaginary component of the power. And then the apparent power is the hypotenuse there, the magnitude of the power, apparent power. So if you have something that says it's a 5 kilowatt load, that is telling you that the real power on the load is 5 kilowatts. If you're told that you have 5 kiloamps load, then that is telling you the apparent power, VRMS, IRMS, is equal to 5 kilovolt amps. And if we have something that says absorbs 5 kVARs, then you know Q is equal to 5 kVAR. And here is what is known as the power triangle, so you can see what this actually means visually. So we have, for an inductive load, the theta is a positive, meaning that the current is lagging behind the voltage. Theta V minus theta I is positive. The phase angle on the voltage is greater than the phase angle on the current. So therefore it is a positive angle, and you end up with power being, having a real number, and then Q being a positive value. And then that tells us here, we have our hypotenuse here, the magnitude, if you will, is VRMS, IRMS. This is your apparent power, real power, and the imaginary or reactive power. And if you have a capacitive load where theta is negative, that's a case where the voltage is, say 10 degrees, but the current is leading in theta. So say we had 10 degrees, but the theta in the current was 20 degrees. And so now we have a power angle of minus 10 degrees. So theta is negative. So again, if you're lagging, your theta is positive. If you're leading, your theta is negative. And here, Q happens to be negative power. And again, these are in units of VARs, volt ampere reactive. So again, lagging would be this, leading is this. So if you ever see a question that says, Q is, 5 kVAR lagging, then you know that Q is positive, and effectively you're looking at this type of triangle. If you have, Q 5 kVARs leading, then you're going to be using this power triangle with the theta being negative. So here's some relationships to impedance. So we have the magnitude and phase angle of our impedance. And of course, impedance can also be in the real and imaginary form. So again, polar and rectangular. And I emphasize over and over again here, I know I've mentioned this several times, it is very important to get used to working back and forth in the two different types of phasor relationships. You have the phase angle and magnitude, are known as the polar form, and then of course dealing with the actual complex form of the impedance being in a real and an imaginary form, where R is the real component and the X is the imaginary component of the impedance. So you can determine, the cosine of theta is R over the magnitude of your impedance, and the sine component is X over the magnitude of the impedance. So nothing really surprising there. Again, this is all out of the basic phasors relationships. And just drawn simply, we have this triangle here where you have the magnitude, real and imaginary. And so power is I squared R. or also v squared r, and granted we're using the RMS, r with the magnitude here, r squared plus x squared here. And then q is equal to I squared RMS x, and we have v RMS squared x over r squared plus x squared. So here's if you're given an impedance and you're asked what is the power, and you only have one of the values like IRMS or VRMS, now you're able to solve using your I squared R and V squared over R, or in this case Z type equations. So we've been looking at all this, and so far we have this equation here for power is equal to VRMS IRMS cosine of theta. So this is a real power. And we know that power is equal to Vm, where this is magnitude, and current magnitude divided by 2 is cosine of theta. So these are equivalent, and we know that. And we also have that the reactive power Q is VRMS IRMS sine of theta. And of course, you could also write it Q is equal to Vm Im over 2 sine of theta as well. This also applies. Where theta, again, is just the difference. It's the net difference between the phase angles between the voltage and the current. So how do we write this in phasor form? You know, because everything we've been working with is mostly in phasors, and it would be really useful to just go ahead and compute power using the phasors straight out. Naturally, we would just say power is equal to V phasor times I phasor. You know, bold V times, you know, I bold. You know, just simply write that out. But that's not how it works out. So let's go ahead and take a look at how we can do this, and this is known as complex power. You know, actually just get straight to the vector instead of the individual components, because that's how we've been working with things so far. So we want to do this in terms of course, voltage and current as phasors in their complex form straight out. So as it works out, the equation for that is a complex power, and it has the value S, just so we can separate it from everything we've talked about so far. And it's equal to 1/2 V times I asterisk. And so some students, there's usually in a classroom, there's usually 1 or 2 students in a group of about 50 to 100 that really know what this means here right off the bat. Because this is typically a sophomore level class, a higher sophomore level class. And so you probably haven't been exposed to this, or if you have, it's probably, you know, maybe been in high school algebra 2 or calculus, and you probably saw it, didn't know really what it was all about. Why would you use this? This is known as the complex conjugate. And so now remember, one of the things we talked about is everything that's going on is about the phase difference. Emphasis there on difference between the voltage and the current. So like I said, we can't just simply take voltage times current, because we're really looking at the phase difference. And that's what the complex conjugate really is about. So just to define what the complex conjugate is, because it's an imaginary, a complex imaginary property mathematically. So if we go ahead and draw a vector I in this case, and it has, here we have, you know, it has this value z plus x plus iy. Let's pretend this is our current here. That it has this vector here. It has x component and it has a y component in the imaginary axis. And so we have this vector here. The complex conjugate, which is, in this case, we have an, simply you know, a bar over z, but this is also can be z asterisk, is the same real component, but the imaginary component just changes sign. So instead of plus yi, it is simply minus iy, or j in our case. So it is just flipping the sign of the imaginary component, basically just mirroring it over. So that's all that the complex conjugate is. It's just taking whatever you had for I and just taking the imaginary component and flipping it. So, and that is due to the fact that what we are desiring is this phase angle, because if you notice we're multiplying. And so just to kind of sum that home just a little bit here, because I've had some students that wonder why we do this. You know, again, in phasor mathematics, if I've got, let's just say A, and we have that as, let's just say A plus, we'll do, let's see here, A plus, let's do what, xj, right? That is our complex number. I'm just trying to pick numbers that make sense here. So we have A, and then we have B, and its value is B plus yj, okay? And if we take A times B, we would take the magnitude of these, and of course we can combine these, and we'll have A squared plus x squared, and we get the phase angle, and we'll get some magnitude. We'll call this AM, and then we have the phase angle, which is theta, for that is equal to tan minus 1 arctangent, if you will, of the x component here, the imaginary component, over A. So we could rewrite this also as A magnitude times its phase angle, A. And then we'll rewrite this one here is B magnitude phase angle, B. And so A times B, and I know I'm probably, boring you a little bit because you've already been doing this for all the homework and everything, but I'm trying to show where this is leading. So we multiply. What do you do here? You add the angles. So you got A plus B. So this is where the problem lies. We don't want to add the Fangus angles, as what we were learning earlier in looking at the trigonometric identities for power. When we do P is equal to VT times IT, which is what we're wanting to do. This is the real physics. This ends up requiring that we have this net phase difference of voltage minus the current. So that's what we need. But if we do simple multiplication of A or B, or in this case, V and I, we end up with this positive here. Well, we can't have that. However, if we take the conjugate, now we end up with this, which does provide us the ability to do this. We're just flipping the imaginary component. So that's what all we're doing here mathematically. It's a mathematical, if you will, trick. It's not really much of a trick. We're just using a mathematical property to get us the actual power that we're going. Because our goal is this, V of t times I of t. You just can't simply take V times I as a phasor to get there, because we'd end up adding the phase angles and not subtracting them. So that's what's going on here. Probably a long explanation for probably you might not have had that question, but it's come up a few times. Why are we doing this? So that's why we have the complex conjugate there. What you need to know to be able to solve this is if you're given what is the complex power, like what is the true vector of the power, you just take 1/2 times V times I conjugate, and you've got your answer. So here's just some simple, straightforward equations. If you've got V and I straight out as phasors, then you take 1/2 V times I conjugate, which is 1/2 Vm times Im, times the magnitude difference between, basically two magnitudes multiplied together divided by 2, and just the phase difference. And that will get you the complex power. You can also get it by using VRMS, IRMS, and all you've got to do is just take the two RMS values, multiply them together, magnitudes, and again, just have the phase angle be the difference. This is probably the simplest equation, because a lot of things you'll be given RMS values. And then if you just know the phase difference, again, this right here is your power factor angle, your power angle. So VRMS, IRMS, and your power angle, and now you know the complex power as an equation. All right, so let's go ahead and just do an example problem here. So here we have a power supply that's 10, phase angle of minus 90 degrees. We have an inductor. We're going to go ahead and just put the actual values in. not go through the solving of what the complex impedance is. So we just have J100. We have a current here, I of C, that's going through the capacitor. That's 0.1 minus 90 degrees. The current going through the resistor is 0.1 minus 180 degrees. Capacitor is minus J100. And the loop current going through this loop here is 0.1414 with a phase angle of minus 35 degrees. So using the equation that we just learned, which is S is equal to 1/2 VI conjugate, we can solve for all the power that we want in this particular problem very easily because we now have all the values. So everything that you've been doing thus far in all of the equations and all of the mesh current analysis and the nodal voltage analysis, so on and so forth, now is giving you the ability to get these values, and now you're going to be able to use that to solve for the power using this formula here. So we now know that V is equal to 10 phase angle minus 90 degrees, and the current is 0.414 with phase angle of 35. So we can actually solve for the power being provided to the circuit. So like what is being supplied by this power supply by just taking V and I, multiplying the two together, and we're going to get the supplied power, but we just first need to take the conjugate. So I conjugate in this case is just changing the direction on the phase angle. So instead of minus 135 degrees, it's just now positive 135 degrees. That's all we had to do to take the conjugate of this. So again, this is kind of the advantage of doing things in polar and in a rectangular. If this was in rectangular, you would have the real component, and then you would just change the sign of the imaginary component. But in this case, we just had to change the phase angle. So I conjugate 0.1414, 135 degrees. So S is equal to 1/2 10 phase angle minus 90 degrees. So the V times the I conjugate, which is 0.1414 phase angle 35. We do traditional math at this point because we've already taken the conjugate. So now we're going to just multiply the 10 times the 0.1414 and add minus 90 plus the phase angle 135 degrees. And we get, and of course divide the magnitudes by 2, and we end up with 0.707 with a phase angle of 45 degrees watts. Again, complex power, since this is now a vector, a complex value, it just has the units of watts. So embedded in that complex value is the reactive and the actual real power in watts. And you can calculate the magnitude of S gives you the apparent power. So in the broken down here, we've got the P term and the Q term. So the P is the real component, which is half a watt, and the Q 0.5 is half of a var, because this is the reactive component. Now again, in a complex, if you will, vector form, this has units of watts. If you took the magnitude of this, which is this 0.707, this part here only, the 0.707, if you were going to describe this, what is the apparent power of this power supply? What is being supplied? The apparent power is 0.707 volt amps. So this has the units of volt amps. This entire S has the units of watts, but the individual component here, power, has got the units of watts, and the reactive power part, the imaginary part, Q, is a var, or half a var. So in summary, we discussed inductive and capacitive loads and resistive power in AC circuits. So just purely inductive, purely capacitive, and purely resistive, and what that looks like. Of course, in actual circuits, we know that the loads are complex. So that just sort of gave us an introduction to it, and we looked at the general case of an RLC circuit. Of course, we talked about what average power was. We looked at apparent power, reactive power, and all the meanings thereof. So we have real power, apparent power, and reactive power. We have the power factor and power angle that we discussed. So a power factor is a number between -1 and 1. And that's just the cosine of the power angle, and you can also be given in percentage, but also discussing whether or not the current is leading or lagging. So if it is lagging, that means the current um, is the current waveform, the phase angle is lagging behind the voltage waveform, but so that the phase difference in the angle, the power angle, is positive because it's phase of the voltage minus the phase of the current, and now that's positive, which means the phase angle was positive, or the voltage was greater than the phase angle of the current, so it's a positive value, the difference. And of course, if it's leading, it's the other way around, so that you have the current waveform is ahead of the voltage waveform, such that the phase difference is now negative. So that's your power angles. And with that, we talked about the power triangle, showing that the hypotenuse was the apparent power. We had the units of watts for the real component, the P, and that Q was the reactive power part. And then we talked about complex power, where we actually used purely phasor arithmetic and how to get to the complex power, if you will, as a phase vector, and able to then pull the individual components out of that. And of course, that required using the complex conjugate. So if you have questions on this, please come to the Q&A and we can talk about it and work a few more problems. Thank you.